Okay, so I think we will get started so we don't run over too late, and hopefully more people will come along as we go. So welcome and thank you for all coming along this evening to our second Tethys seminar. My name's Will. I'm co-hosting it this evening with Safi, who's at Cambridge. So I apologise to anyone that came last week and has to listen to me do the little speech again, but a few bits of housekeeping before we start. So each of the talks will run for about 15 to 20 minutes and will be followed by a short period of questions. Please enter any questions that you have into the chat during the talk and we can read them out for you. I'm also going to put a feedback survey in the chat at the beginning this time, and feel free to just click on that link and fill it out at the end. So some of the feedback we got last week was that they wanted more questions. I can't really facilitate that with kind of asking infinite questions, so feel free to ask questions and get involved. But we do also know that it can be a little bit intimidating to ask questions in front of a group of people that you don't know. So if you want to message myself or Safi privately and anonymously, we can ask the question for you. The more slightly serious bits, so everyone kind of agreed to a code of conduct when they signed up. So if you can make sure that the videos are switched off at all times unless told otherwise, just to make sure there isn't too much latency on the call, and microphones as well to remain muted. Importantly, Tethys seminars are provided as a platform for young geoscientists to present their research within a safe setting, independent of race, gender, religion, sexuality or background. So we want all attendees to behave in a professional manner. And any actions or comments that may reasonably be considered disrespectful, discriminatory, or compromise the safe and inclusive nature of the seminars is forbidden. This includes comments during or after the seminar, during questions, during feedback, or any other related posts on social media, such as Twitter, Facebook, LinkedIn, or YouTube. And anyone that violates that will have to be removed. So that's the kind of not very fun bit. Onto the more fun bit. So I'm excited to kind of introduce our first speaker, who is Ashar Aslam, who's at Oxford. So he's in his 4th year and doing a master's, having done the bachelor's at Oxford in Earth Sciences as well. And is showcasing some of the work that he's doing as part of his master's this year, but also as part of a studentship with the Met Office over summer. So Ashar, if you want to share your screen and go for it.
Yeah, sure, I can do that. Is it showing? Yeah.
Might be in a minute. Yeah, there you go.
Yeah, I'm screen. Okay, so I'm presenting some stuff I did over the summer with the was a studentship offered by the Met Office Academic Partnership, which is formed part of my master's project, which has there's a more complete title to this project, but this is the limit as to where I'm going with it. This was quite a lot of segmentation with what I've done so far. So if I go to the next slide. So the first thing is, why should we care about tropical depressions? Well, the obvious thing is they have had significant impacts on communities' livelihoods. So in any region of the world, so you've had Hurricane Sandy, Cyclone Nargis, there's loads of them around the world. And if we can improve our understanding of these dynamics, we can help with disaster mitigation efforts through forecasting. And these need to be good enough for universal applications. So in areas where there's like maybe lower social and economic status, where they don't have access to state-of-the-art climate models. So if institutions elsewhere in the world can provide these to those countries, that's very critical. And we also need a better handle on cyclone energetics, given the effects of global warming and climate change on the frequency and intensity of global extreme weather events, which includes tropical cyclones themselves. And knowing the atmosphere is inherently chaotic, this is even more crucial. So this slide is from Tran et al. And it basically shows 2 of the climate models created by the Met Office. So on the left-hand side, you have the RA 25 kilometer model. And as you can see, it gives like a good picture like precipitation and solar radiation. So that the precipitation is the bottom color bar, and the top one is the solar radiation. And on the right-hand side, you have CP for Africa, which is their updated model. So it's higher resolution. You can visualize more meteorological phenomena. So around the Congo Basin in Central Africa, you can see that there's more propagation of these thunderstorms, whereas in the left-hand diagram in RA25, you have this rapid pulse, which doesn't really give a handle on to what is actually going on in these systems, because on the right-hand side, you can see a slight rolling, which is due to the evident vorticity of these storms. Next slide. And so for my project, for my master's, I'll be focusing on the CP4 African model. And this is the diagram from a geography student who graduated last year at Oxford, and this is from her dissertation, and she looked at how in convective permitting simulations in the Mozambique channel, so you can see my cursor, around between Madagascar and Mozambique. So TAMSAT is studied for land mainly. The MIARE 25 incorporates some ocean measurements. But as you can see on the far right-hand side, you can see there's some incredible bias and intensification in the Mozambique channel. And just to give an explanation, the color bar for cold cloud duration, that basically means how long a pixel has been colder than, I think it's around -50 degrees at the top of the cloud. And so it gives a daily measure of convective instability in the system by using that proxy cloud top temperature. And that's determined by the Stefan-Boltzmann law. And satellites can detect this from the brightness of the clouds as when they scan over them. And that's a proxy for the duration of these storms and their intensity. So to give an idea of these biases, we need to find a case study. So for my project, I'll be looking at Cyclone Idai, which is one of the most catastrophic tropical cyclones on record in terms of the damage and implications it had and the intensification processes. So the 914 millibar low, sustained winds of 125 with gusts of 175, and it killed over 1,000 people, affected millions, and obviously caused billions of damage. And in the diagram on the right, you can see the track of Idai. So it started in just off the north coast of Mozambique. It then tracked inland towards Lake Malawi, and then gradually propagated eastward towards Madagascar. And while it incorporated some dry air then, once it started propagating back over the channel towards Mozambique, experienced rapid intensification. So you can split Idai's life cycle into 3 distinct portions. So from the 4th to 7th, you have the formation period. Now was when it originated from Tropical Depression 11. And then from the 8th to the 11th to 12th, you have the shift across the Mozambique channel towards Madagascar. And after this, you have the intensification as it continues to travel over the channel, reaching peak intensity, I think it was on 13th of March. We don't include the 16th of March till the 21st of March in these simulations, as will be shown later on for obvious reasons. So the first thing I have to explain, what is moist-static energy? So it's thermodynamic variable calculated by lifting air adiabatically to the top of the atmosphere and allowing all the water vapor present in that parcel to condense and release latent heat. So it's split into 3 terms. So if you can see on the equation, that's representing MSE. You have a heating term dictated by the specific heat capacity and temperature, a height term determined by geopotential, and a humidity term, which is represented by latent heat, vaporization, and specific humidity. And one thing that makes the MSE so powerful is that during adiabatic ascent and descent, it's conserved. But however, and so in this diagram, you can see that conservation. So it's a little thing I made, like a little ocean, low pressure system. It's a very simplified model of convection and how the energy can come into play. So as you rise from a low pressure to high pressure, you gain the height, so that's an energy term, but you cool the parcel and lose humidity through, you lose that humidity through precipitation. And that continues along and then comes back down to the high pressure. And then once that you're traversing back along the ocean, that's where you pick up that humidity again, and that provides a fuel for the storm. And so the good thing about cyclones is that MSE isn't conserved. So you can use it as a way of finding sources and sinks of energy into the system, so what fuels it and what dissipates the energy from the system. So one key term is this LQ at the bottom, and that's basic property for latent heat, and that's carried along by the strong winds associated with tropical cyclones, and that's brought quickly into the system and then brought up, and then the process continues. And this red stippled line, that represents the area I'll be focusing on, because we're only focusing on lower tropospheric processes because those are the ones that directly affect society and communities and general livelihoods. So you'll see that further on with explanations in some of my plots. So brief rundown of methods. So I used the ERA5 dataset, which is provided by the European Centre for Mid-Weather Forecasts, and that was to develop a convective parameterized simulation, which will be used later on to compare to the convective permitting simulation, that is CP4 Africa. And on the right, you can see the rough target regions. So in the plots later on, you won't see these latitude and longitude lines because the number of plots made it quite congested. And the grid spacing was 0.25 degrees resolution, really good for studying this. And it was computed for the 12 days as specified in one of the previous slides at 6 p.m. Where there's still humidity in the atmosphere, but solar radiation is pretty much negligible. So in these two equations, the top one represents the MSC budget. So going through it, you have the horizontal advection and vertical advection, and they act to remove MSC from the system. And then you have latent heat, sensible heat, outgoing long wave and short wave radiation. And those act to add energy into the system via the heating. But we'll be neglecting short wave radiation in this computation. And the bottom, you have a humidity budget, which is usually multiplied by the latent heat vaporization to get into a scale that can be compared to MSC. So you have the horizontal and vertical advection again, as well as precipitation and evaporation. So they'll come into play on top of that. So there's some previous studies that incorporated these budgets. So one was took the Madden-Julian oscillation, which is a climatological feature, which is similar to other oscillations in that it can dictate rainfall, anomalous quantities of it. But the difference of it to, say, the El Nino and Indian Ocean dipole is that it isn't a fixed system. It basically propagates eastward along the Indian Ocean towards the Western Pacific. And Kiramani and Maloney, they showed that you can use this budget to identify the different phases. And then Wing, she compared different existing climate models using the budget to analyze their sensitivities in terms of their lifetime maximum intensity and identifying the rough cyclonic structure in the lower troposphere. I'm just going to highlight that this is probably one of the first times that people have used the MSC budget for forecasting purposes. So looking at cyclone formation, intensification, and I'll be giving like a more top-up, well, the radar gives more of a top-up view, but I'll be giving more of a top-down view in that we'll be looking into like the bottom half of the cyclone rather than the whole picture that only radar, well, what satellite gives you, because it only views it from the top. So this is the first plot I have, and I'll just run you through these plots. So from the 4th to 8th, you don't see much. The MSC budget isn't that strong, although you tend to see some hints of it to the east of Mozambique, just like in the northern part. And then as you go to the 9th of March, you start to see a buildup of MSC, which is associated with the initial stages of Idai. And then as it's turning back westward towards Mozambique, you can see from the 11th to the 13th and 14th, it's intensifying. But one thing you can notice, and it's quite strange, is that from the 4th to the 8th and the 15th, you don't seem to get a signal for Idai, even though it's of weak intensity. There's just no hint of like its landfall or what it's doing there. I'll be touching on that later on. That's why we didn't compute anything for the 16th to 21st, because that's when it was primarily over land, so nothing was showing up in the data. And then to compare, we use the humidity budget. And as you can see, this gives a stronger signal for the tracking of Idai over land as well. So it like seems to coalesce with the position of Idai when it's over the ocean, but say on the 4th to 6th and the 15th, you can see there's a distinct feature over land. And that's probably due to the precipitation and the associated latent heat produced from it. And that's what's supplied to the, that's what's being removed from these systems. As you can see, the scale bar has been shifted down. So the more blue it is, there's more precipitation, assuming more precipitation, more latent heat is lost from the system, and therefore less of the humidity budget. And this is basically a comparing the terms in the MSC budget. So you want to ignore the bottom half. That's just, I'm not entirely sure what that's due to. It may be due to this intensification of the subtropical ridge southwest of Idai during the same time, but not entirely sure. But what you can see is that the advection terms pretty much have no significance into the overall budget. And sensible heating doesn't really do much because sensible heating is derived from the difference in temperature between the ocean and atmosphere. But here in the tropics, the ocean atmosphere are pretty much the same temperature, so the surface sensible heating flux is not really significant. But what you can see, and it's really well shown, the latent heating flux, is that there's a strong contribution from latent heating to the MSC budget as it acts to warm the column. And the converse can be seen kind of with the outgoing long wave radiation, where it kind of produces a cooling effect. And this can be explained by simply just clouds. So usually you'd have the surface outgoing radiation and the top outgoing radiation, and usually the difference is significant. But with a cloud impeding the transmission of the surface radiation to the top, you have it absorbed by the clouds and then either re-emitted to the, it's absorbed, re-emitted to the atmosphere or re-radiated downwards. And if you think of it in terms of vectors, you basically have them counterbalancing. So where they counteract, and that reduces the surface heating outgoing thermal radiation. So you'll get a lower contribution to the MSC budget where there's significant clouds. And here are just some diagrams showing the different advection terms. Surely, well, you can see it's, with the horizontal advection, it's very chaotic. There's no real distinct pattern, although you can see kind of some circulation, but it's not at all, well, it's not strong enough given that the magnitude is 2 orders of magnitude less than the overall MSC budget at least. But the vertical advection shows how like a grade 1 order of magnitude greater than the horizontal advection. And you can see that with this distinct formation of positive vertical advection around the eye wall. And that's where you're having the vertical rising of moisture as it's lifted up via lower level convergent and upper level divergence in the atmospheric system. And that's why you get that distinct feature around the eye wall. And then looking at the terms in the humidity budget itself, you can see there's the strongest correlation between the humidity budget and a term is that latent heat produced due to precipitation. And that's what's accounting for that supposed discrepancy in the MSC budget. You're lacking that extra humidity source and sink. We don't have the humidity source anymore, but this humidity budget is so sensitive to it that it shows it to a greater level in some way. And you can see in the vertical advection, there's a slight kind of ring structure around the eye wall, which suggests there was some downward export of that humidity, which is probably coupled to that precipitation term. And then you have these little terms in the MC budget as well as that humidity term. So I've used an overlay of the, I think it's the minus 1,000 watts per meter squared contour for humidity. And you can see that the missing term is directly can be attributed to that precipitation, because on 60 you expect the storm to be around Malawi, where there's Lake Malawi there. And in the bottom, you expect it to be just inside south Mozambique. So you can use the humidity budget as a proxy for where potentially Idai was located, but there's still some uncertainty about that. So in conclusion, you can see that the budget framework has been shown to be quite valuable for showing the cyclone, specifically Idai in this case, and its processes oversea. But it obviously fails over land due to the lack of that humidity source. And that's where the humidity budget comes in with its importance in highlighting those discrepancies. And you can see that the latent heat flux and net column integrated albedo long wave radiation are the most dominant components, with the latent heat flux the strongest. Well, going back to the moist static energy slide, where you have that advection of the latent heat by the strong surface winds attributed to the cyclone itself, drawing in all that latent heat and then bringing it up into the system. But even though you have those discrepancies, it'll be as a whole useful given the biases in C4 Africa and how they're confined to the channel. So it's hypothetically due to coupling between the ocean, the atmosphere, and the transfer of humidity, and maybe they're more sensitive to that. We don't know, but that'll be something that'll be covered later on. And one question I had to myself was if it's useful in continuous forecasting, particularly on landfall, because obviously it fails there. So can you use this energy like dynamic term to show where a forming cyclone could end up and where it may end up on land? And there's a website you can use to look at like weather systems called Ventusky, and that gives like really good like radar view of the cyclones itself. And I'm just curious if there's like a time lag in the budget changes and where the cyclone is present at that time, because although you get the distinct structure as you move around the channel, whether Idai is actually located though, we don't know, because there may be a time lag. Maybe looking at more hourly plots rather than daily ones at the same time could prove helpful. And so just going to the remainder of my master's project, so watch this space in case I end up doing another one of these, who knows. So the next step, next week, I'll be applying the budget framework to the CP4 Africa dataset given by the Met Office. And basically we're just identifying the formation of those cyclones by looking at values of relative vorticity, so like the spin and curl in the system. And I'll be used to identify the biases and relate them to the energetics in the system. And even though we have those biases, we may try and see if those biases have actually a justification, because with global warming, you're getting warmer surface waters. That can lead to warmer surface, like lower atmosphere temperatures, which means they can take up more moisture, or more water vapor, because they have greater heat bulb. They can take up more moisture from the ocean. Took me a while. And we can see if they have some effects on the intensification of weakening cycles and the lifetime maximum intensity of those cyclones, given some of the studies as shown in the citations. But yeah, thanks for listening. And if you have any questions about my project or even the studentship itself, I'm happy to take some questions. So yeah. Want me to stop sharing or?
Yeah, maybe keep it on for a minute in case there's questions. That,
I have a question, if that's okay.
Yeah, Tam's, yeah, go for it.
I was, when you were talking about forecasting, like using MSE for forecasting, and you were saying that like one of the reasons it might not be so good was because of the fact that it's not so good over land. I was wondering about like how good is it as a kind of early warning, because when you were showing the comparison between MSE and humidity budget, it also seemed like humidity budget actually showed the storm earlier in the day than MSE. So I was just wondering what your thoughts were on that.
Yeah, I'm gonna have a look at that. So yeah, I can see what you mean, and I think that's due to the precipitation effect. But I don't know if there's any current models which use these energetics to forecast the incoming cyclones. But obviously with Obviously, the North Atlantic hurricane season, they're in Greek letters now. It's quite extreme, and that's possible implication of global warming, but we don't. It's still under research. And knowing that these energetics are so chaotic, whether they're reliable in forecasting, we'll have to test it out, but there's no, I don't think the MSC budget has been used, or the humidity budget has been used in forecasting, because that requires some predictions of the humidity itself and the MSE and all the individual terms involved in it, because there's a lot of different parameters you have to incorporate. So it can be quite complicated. So people tend to just, I think, use simple radar, where look at the relative spin of velocities in the cyclone and core itself and see where it could propagate. And that's why in, say, hurricane forecasts, you get like a diverging potential location of where the cyclone could go, because there's so much uncertainty. So it's something that could still be looked into, but there's no real certainty as to whether it's viable at the moment.
So it's more like, it's more interesting in understanding after the event of a storm, like the dynamics of the storm itself while it was over the ocean, generally. Yeah, and
this can be used later on, because some cyclones show similarities. So there was some, I think it was Cyclone Helen, which hit Mozambique, I think, in 2004. And it followed a similar pattern in that it tracked to Mozambique, went back to Madagascar, and went back along the channel. So using those like proxies for like, what's the word? As like a representative model of future potential cyclones, it can be quite useful if we know what the surface and low atmospheric conditions will be like in the coming days. So it could be, it's an ongoing area of research, I think, but it's quite exciting in that, well, knowing what these forecasting tools could do in helping like disaster mitigation. So anything that can be done will be useful.
Yeah, really interesting. Thanks.
Saf, am I okay to ask a question quick? Cool. Okay, so thanks for doing the talk. It's really interesting and has reminded me how far behind I am on my project, so thanks for that. I'm just wondering, maybe this is quite a quick question in comparison, but you said that when you were putting together the equations, you took out the shortwave radiation, I think.
Yeah.
Is there any reason behind it? Is it just because it's negligible, or?
So obviously with the solar, it's dictated by solar radiation, and I did look at some of the time, I did make some plots in the past looking at the effects of shortwave radiation, and it didn't really do much. But there were some previous studies which kind of just said, solar radiation doesn't really have a control on the formation or intensity of cyclones. It's mainly dictated by the latent heat and the thermal radiation. So there was a possibility we can see what it does, but I doubt there's any real impact looking through like simple data values that were provided by ERA 5. So yeah, it was pretty much negligible.
Okay, cool, thank you.
Yeah.
Okay, it doesn't look like there's any more questions at the moment, so I guess we'll move on. If there are any more questions, then feel free to pop them in the chat and we can read them out for you after the second talk. So just to move on quickly to the second talk, so I'm kind of excited again to introduce our second speaker, which is Alasdair Knight. So Alasdair did his undergrad at Bristol, then moved to Cambridge to do his master's under Dr. Edward Tipper and Dr. Emily Stevenson, and is now working with both of them on his PhD at Cambridge as well. So Alasdair, if you'd like to share your screen and go ahead with your talk.
Yeah, of course. Can you hear me okay? Is the volume okay?
Yeah, it's perfect. Yeah.
Perfect. Nice. Okay. So I'm going to be talking about, hopefully this works, longer term CO2 drawdown, maybe on geological timescales. When my computer screen loads the presentation, there we go. Okay, so thank you for having me, and thanks to Will and Safi actually for setting this up. It's a really good idea to have some grad talks. So yeah, as Will said, I did my master's project last year, so I'm going to be talking about, well, I'm going to try and convince you why I think that estimates of CO2 drawdown by silicate weathering are wrong, and it's all due to mud and water. So hopefully by the end of this talk, you might look at a muddy river a little bit differently, or at least I do. Okay, so I've assumed very basic knowledge of theories like BLAG. So if you've covered that, you'll probably know this potentially better than I do. But here we have so the silicate weathering equation and carbonate weathering. So the basic premise is that if you look at these kind of nasty looking equations, for silicate weathering, you're removing 2 moles of atmospheric carbon dioxide, and one of them is going into a solid form, calcium carbonate, and one is going back into the atmosphere. Whereas carbonate weathering, it initially draws it down into a liquid form or a dissolved form, but then the CO2 is released back into the atmosphere. So on very long timescales, we care about telling silicate weathering and carbonate weathering apart. Now it'd be really useful to be able to trace carbon. Obviously, if we could track carbon through rivers, then that would be, well, I'd be out of the PhD actually, but that'd be really good. But instead, we can't do that because it's quite difficult. So we track elements like calcium, magnesium that form the carbonates as a tracer for carbon. But the problem with that, as you can see from these equations, is that both silicate weathering and carbonate weathering released calcium into solution. So some very bright people came up with the idea of normalizing to an element that isn't found in carbonates as a way to tell those lithologies apart. This again, kind of scary maths, but this is how they came up with the plot. There's lots of different ways of coming up with estimates for silicate and carbonate weathering. This is called the inverse model. There's also something called the forward model, which is a bit easier to explain, but this is kind of the modern approach to estimating these weathering fluxes. As you can see, they're normalized to sodium, but what they haven't included in previous estimates of silicate and carbonate weathering fluxes is this exchange term, which I'll come on to explain later. Here you can see I've plotted the 60 of the largest rivers in the world by discharge on this plot. And you can see that lithology is a strong control on the chemistry of these rivers. Okay, so now moving on to cation exchange, which is the thing that I think will have changed the chemistry of the rivers and made these estimates of CO2 drawdown incorrect. So I'm going to introduce some terms here. It's probably worth paying attention to these terms because I will repeat them occasionally in the talk. So the elements that are, so in cation exchange, it's often on clay minerals because they have a lot of negative charges I've drawn really crudely here on clay minerals. These are due to isomorphic substitutions, or basically they've swapped for another element in the lattice and they've got a negative charge. So in solution, you get dissolved ions which stick to these negative charges, dissolved cations, as you can see by the sodiums here. And the elements that are on the clays are called the exchange pool. And you also have, obviously, in water, you have dissolved elements, cations. So one of the fundamental things you need to know about cation exchange is that you need to keep the charge balance the same. So if you exchange a calcium, you're going to remove 2 sodiums. And likewise, if you exchange on a potassium, you're going to remove a sodium. So this is kind of a continuous reaction that occurs rapidly throughout water. So when I was saying that you might look at rivers a bit differently, this is occurring continuously all the time. So now we'll get on to my experiments. So this is as far as fieldwork as I got last year. Some people went to the Himalayas with my supervisor. I went to Sainsbury's. But there's a good reason for this, which is that rather than collecting rivers from around the world, it was actually a lot cheaper and made the experiments more reproducible if I went and got bottled water, because the ratio of cations or dissolved elements in the water was very similar to rivers, as you'll see on the next plot. So there's, if you've ever wondered where Buxton in terms of calcium, magnesium and sodium plots next to some very large rivers, then now you can stop watching the presentation. But as you can see, they form an array. along the world's largest rivers, which is quite helpful for looking at them. And you can also, you could have guessed that because they're also got a strong lithological control. So I also needed some clays. The only point of this figure is really to show that there's lots of different clay structures. If you've never come across a clay or never looked at a clay mineral, it's silica in tetrahedral coordination, and often a cation in octahedral coordination, and they're bonded together. And you get lots of different layers. I will show in the next diagram. So here's some nice SEM images I found today. You can see these kind of layers in the clays. And I also needed to vary the water to clay ratio, because in rivers in a natural environment, you have different concentrations of sediment, which will affect the exchange process. Okay, so I'm quickly going to go through the methods so you understand my results a bit better. But initially, I saturated the clay in ammonium ions. If you noticed, I've tried to keep, provided my maths is correct, I've tried to keep the charge balance the same. So I initially extracted all the elements off the clays that I had and measured that just out of interest. I then added the bottled water to the clay and let it equilibrate to see which elements were going onto the exchange pool. If you remember, the exchange pool is the elements that are on the negative surface charges of the clay. And then I measured that solution. Obviously, the difference between what's gone on and what's remained in the water, the difference between the bottled water and what's remaining in the water has gone onto the clay. And finally, I extracted that back off again, just to double check that what had definitely gone on had been via cation exchange and not another mechanism. Okay, and this was all done on an instrument called the ICP OES, which measures the composition and the magnitude of the exchange flux. So these are the results. I'm going to introduce another term here, which is the cation exchange capacity. It's the number of positive charges per unit mass that's exchanged. So if you've got a calcium, you've got 2 positive charges. So it's a nice way of comparing different exchange methodologies. But in my experiments, the clays were so efficient at removing cations from the water that they literally stripped the water of all the cations. So as you'll see in the next figure, I've plotted the potential exchange capacity against the measured, and you can see it plots on a 1-to-1 line for some of them. All that's saying is that it's basically removed all of the cations from the water, so you're limited by the number of cations in the water itself. Okay, and this is the more interesting figure, I think, which is comparing competitive exchange. So you're looking at which cations have an affinity for the exchange pool and which ones remain in solution. The 1-to-1 line, which is kind of a little bit hard to see, simply says that there's no exchange, there's no preference for either. You've got the same concentration of cations on the exchange pool as you do in solution. If you look at something like calcium and magnesium, you can see it plots kind of fairly nicely on the 1-to-1 line. Whereas if you look at the divalent and monovalent diagram here, they're just expanded. This is just this area expanded in the bottom. You can see they all plot above the 1-to-1 line. And the beta is for the exchange pool. So what this figure is saying is that on the exchange pool, you've got a lot more calcium than sodium. And in the water, you've changed the ratio of calcium to sodium such that it's got lower. So the divalent cations, i.e. the ones with 2+, are going on to the exchange pool, which will be important for later. So you can see that visually on this diagram that I showed you at the start, where all the world's rivers were plotted. And you can see that these diamonds represent the initial water composition, and the circles represent the water composition after exchange. And you can see that they've moved from the carbonate. I'm sorry it's not labeled, but there's a carbonate end member here, and they've moved towards the silica end member because the sodium in the water has increased, because the calcium and magnesium has gone onto the exchange pool. And you can see this effect is more pronounced for clays such as montmorillonites as opposed to kaolinites, because they've got a greater number of charges per unit mass. You can also see that a higher concentration, as you would expect, means that you've got more exchange sites, so more of the calcium and magnesium is being removed from the solution, i.e. you're shifting on this diagram further towards the silica end member and even beyond for some of them, some quite extreme shifts there. And also you've got a controlling factor from the initial water chemistry, which is a little bit difficult to see on this plot because it's on a log scale. But that's just saying that if you've got more magnesium and calcium in your solution initially, such as you have in Evian bottled water, then you're getting a greater shift. So what are the meaningful results from this you can apply to the real world? Okay, so in areas with very high suspended sediment, such as where you've got 1 to 10 and 1 to 100 parts, so that's 10 parts water to 1 part clay, or 100 parts water to 1 part clay, you're going to get really extreme shifts in the chemistry, such that you saw on these diagrams. So often they measure the river chemistry during the monsoon season because there's a greater discharge of water. So if you've got a monsoonal river with lots of clay in it, the chemistry that you're measuring to get your silicate weathering and carbonate weathering fluxes is going to be not the chemistry that's released from the reactions. There's also going to be an exchange term. Okay, and then I also extrapolated it during my master's down to lower concentrations. So now you can see the 60 world's largest rivers by discharge, and you can see what the chemistry would have been before cation exchange. I'm actually currently working on this figure to improve it, but the end result is the same, which is that they have been shifted further towards the silicate end member. Hence, we've overestimated silicate weathering and underestimated carbonate weathering, whereas the coloured shapes represent what the chemistry would have been prior to cation exchange. And obviously this has big implications for that CO2 drawdown over longer terms, long timescales, over millions of years. And this is a final figure I created quickly, which is the idea that there's kind of an exchange pool cycle of clay. So in your rivers, you're getting a lot of the divalent cations, such as calcium and magnesium on the exchange pool. And then when this reaches the ocean, we think they exchange for sodiums dominantly, releasing calcium magnesium into the ocean. And then what we don't know at the moment is the sodium brought back up via uplift again, or is there something else going on underneath? So that's kind of a future bit of work to do. That's the conclusions, that the clay mineral matters for the exchange process, the clay concentration matters, and the initial water chemistry matters. For high suspended sediment concentrations, it's a big shift. If you go to lower suspended sediment concentrations, it's not much of a shift, but you get a shift in a lot of the water chemistries. And this will reduce our estimates of CO2 drawdown by silicate weathering and increase carbonate weathering fluxes. Thank you very much for listening. Here's a few of the references that were throughout. Yeah, and if you've got any questions, feel free to ask or put one in the chat. Thanks for listening.
Oh, thanks for that, Al. So yeah, if anybody has any questions, put them in the chat, or you can message me privately, and then I won't say who asked the question.
Whilst we're waiting for any other questions, can I ask, so in your own side, you're kind of saying that it's going to reduce or change the estimates that we get. What order of kind of magnitude of error do you think there is on a lot of those estimates? Is it pretty significant, or is it?
Kind of, it depends. It strongly depends on a number of factors, dominantly being the concentration of sediment you have in the water. So for some basins around the world, I don't know if I can show you this, but basically there's a paper hopefully going out potentially. It's in review at the moment with my supervisor, that's saying that some basins could be reduced by 100% in terms of their silicate weathering flux. I'd say on average globally, we're looking at maybe a kind of a 20 to 30% reduction in silicate weathering from that flux. That's just on initial estimates, but hopefully my PhD will be kind of quantifying that number a lot more, and hopefully getting a much better estimate on that reduction. For anyone interested, the paper that initially started all this, the seminal paper, was by Gaillardet in 1999, and it's quite a good read if you're interested in kind of silicate weathering, CO2 drawdown.
So we have a question from Nikki. She says, is there any way that you can check your results to see what the real initial water concentrations are, e.g. getting water without the clay minerals?
Yeah, so that's not a silly question at all. You can, and there are other ways other than river chemistry of checking kind of silicate weathering fluxes. So the reason we use river chemistry is that it integrates a very large catchment. So you can go to individual sources and check chemistries, but obviously that would be a mammoth task to be able to go to every little stream everywhere and check that. So that's why you use these kind of very large rivers to estimate this, because they integrate a huge number of weathering reactions. So I guess that's you could go and check that, and that's kind of what I'll be doing if I get on any field work during my PhD further than Sainsbury's, COVID depending. Then that's something I will be checking, is the changing chemistry as you go downstream all the way to the ocean.
So we have an anonymous question, and they say, do you know how much this potential error, as in the overestimation of silicate weathering, has been discussed by the IPCC in any of their reports?
So I don't actually. So silicate weathering, I guess, it acts on geological timescales in terms of weathering reactions. That's why you struggle to study these reactions, because they're so slow. So I guess for the IPCC are focusing on kind of enhancing the weathering, silicate weathering flux. You might have seen that they're looking at kind of sprinkling rock on fields and that kind of thing to try and enhance this process. But I'm not actually sure how much they talk about this silicate, kind of the natural CO2 drawdown mechanism, because what we're doing to the climate is far worse than what this would take millions of years to kind of correct our mistakes naturally. So I'm not sure what the IPCC report says on this. It's more focused on kind of potentially speeding up the silicate weathering flux so that it might be useful rather than waiting a million years. But yeah, I'm sorry I haven't got a better answer for that one. Cool.
And we have another question from Serin, who says, it sounds like the timescales that you're talking about won't be affecting our current climate change, but are there any particular proxies that we may be able to look at to understand how this could affect our understanding of previous climate events? They're unsure given the not fantastic record of channel deposits.
Are there any particular proxies that we may be able to look at to understand how? Yeah, so they've done lots of they've tried to model this. So this is the kind of the Blagg hypothesis I was talking about before, where they've tried to have a look at this, so the silicate weathering flux is a temperature dependent reaction. So they've tried to look at how we think climate would have changed in the past and kind of model these reactions. In terms of proxies, they have other proxies for weathering. So you might have heard of the lithium proxy for weathering. So they look at lithium records in seawater to try and estimate kind of weatherability. But that's a very hot research topic at the moment, and there's lots of debate over whether lithium is actually reflecting weathering through time. So there might be other proxies, and if you know of any, you better publish it, because people are desperate for this sort of thing. But yeah, I'm not sure. If I've misinterpreted that question as well, feel free. I think is it from is it Serin, is it? Then I'm yeah. Anyway, sorry for rambling on too long.
Cool. Yeah, I think it's Karen.
And Karen, apologies, Karen.
We've got, okay, brilliant. It doesn't look like there's any more questions. If there are, then pop them in there quickly before I finish talking, which I promise won't be too long. I'm going to pop another link to the feedback survey in the chat, and so this time I'll actually give you some time to click on it before I close the Zoom call, which was one of the major criticisms of last time. But other than that, thank you very much for all coming along and attending this event. We do have another event next week, So feel free to chime in for that, and look out for all of the different social media posts that I'm sure we will be spamming you with. I'm sure you're sick of them by now, but we probably will keep doing it. But thank you again to Ashar and also to Alasdair for coming along and kind of giving a talk, and thank you to everyone for coming along and listening. We hope you enjoyed it, and if you do want to have a rewatch, if you enjoyed it so much, or if you want to have a look at any of our last talks, or the only previous talk that we've done so far, then you can have a look at our YouTube channel, which you can find via our website as well. So thanks again for everyone for coming along, and hopefully we'll see you all soon, and I will promise I will post Yeah, sorry, I've muted myself, but yeah, the feedback thing's in the chat now, I promise. Give it one more minute so people can click on it, and then I'll end the call.